Let's take a look at this application example where you essentially have a steel eye section, right? So it looks like an eye, that's why it's called an eye section. It's not a thin walled eye section. You will see later in this topic we will cover thin walled eye sections where the shear stress distribution is completely different than what we are studying until now. This is not a thin wall. It has sufficient, thin walled in the sense the width of the flange that you see over here. In eye sections, I am not sure if you are familiar with the terminology. This top part is known as the flange. This vertical part is known as the web, and again the bottom part is known as the flange. So let me maybe make a note of that. You will find this terminology useful later as well. So this is the flange, this is the web, and this part is the flange again. Right? So what you are given are these different dimensions, that is the the thickness of the flange, the overall width, which is 300 mm over here, and you have the the central height, which is given 100. Since it's symmetric, as you can see that your centroid is exactly at the center, that is at the neutral axis, that is at 100 mm over here. Right now you're also given the eye, the area moment of inertia. This is something which you should be able to calculate given all the dimensions of this section. I have not calculated that. You can go ahead and calculate and you will see you will get this particular number. Now what this problem tells you, that this steel eye section, and steel eye sections are actually extremely popular for steel constructions in bridges and so on. What this problem says, that here for this steel eye section, here it is subjected to a shear force of 80 kilonewtons. So this V is 80, and what this problem asks you is to draw a sketch of the shear stress distribution across this cross section that you have. Now we have derived it for a rectangle, so this is actually something which is composed of individual parts, that is a rectangle. Now this figure that you see over here is simply the section view of this one. This is the 3D view, this is the section view. So if you're looking from this side, you will see that this is the section, and the dimensions are also marked over here. Now that we have this figure, what are our some of the key points of interest? Because we know a few things until now. The few things we know is that for rectangular cross sections, the stress distribution is kind of parabolic that we have, and it is maximum at the centroid kind of a thing, and at the edges it becomes equals to. So some of the things which we have sort of derived. Now for this one, what are going to be my points of interest? One point of interest will be the top edge and the bottom edge over here, and there we kind of know it is going to be 0. Another 2 points of interest would be, see at this interface over here, there is a jump. Now remember that in our tau equals to VQ divided by IT, the denominator, that T, that is the width. So here you see the width undergoes a jump from 300 mm to 15 mm. So this thickness is 15. From 300 it goes a jump, so you can expect the shear stress to go a jump as well. So maybe at this interface over here, let's just mark 2 points, one just above the interface and one just below the interface over here. So let's go ahead and mark that. The bottom point I have marked as B, and just above the interface I have marked as B prime over here. Now these are another 2 points of interest where I can expect a jump to happen, and then there is not much of discontinuity. Another point of interest may be the centroid C that I have over here, that is exactly at the neutral axis. Now since it's a symmetric section, what we can expect that the shear stress distribution, if I start from the top and reach the center, it is going to be a mirror image. The bottom part will be simply a mirror image of that one. Now so let's write the formula for what we had sort of derived, and at these different points of interest, let's try to write the expressions for the tau which we are going to get. So what we can write over here, that our tau, we know that equals to VQ divided by I times T. So first is at the very top, at the very bottom, since there is no transverse shear, we know at the top and the bottom it is going to be 0. So let's just make a note of that. So at top, bottom, at the top and the bottom tau is 0. Let's come to our next point of interest. So that is maybe B prime over here. Now in this expression, the V is already given, I is for that entire section which is over here, T is the thickness, the width. So at B prime, which is just above, at B prime you see the width of the section is 300 mm. So at B prime I can write that my T is 300 mm that you have over here. And what about the q? The q, again, remember, q is always the for the area above or below. Let's consider the area above. It's easier. Now this b is just above the section, so essentially for b prime or b, you are going to have the same q, because this b and b prime are just above and just below this, this where this width changes over here. So let's write the expression for q. So q, you remember, is the product of the area, that is the area of this part over here. So maybe it's better I probably just mark this area, right? So this area times the distance of the centroid of this area up to the neutral axis. So let's write the expression for that. I will write it. You can verify whether what I'm writing is correct over here. So this is the expression for q that we get. 300 times 200 is this area, and this y bar prime is the distance from the neutral axis to here. You see, this is 100 mm plus this half of this one, because the centroid of this top rectangle will be half of that 20, so it is 110 over here. So at b prime, if you substitute all the values, given that v equals to 80 kilonewtons, I, and you have all the other parameters over here, what you will see that this tau, it comes out as 1.13 MPa. Now let's move to our next point of interest, which is B, which is just below. So the only thing which is going to change, V stays the same, Q stays the same as well, because you're looking at the area above. So if your point B is just below that in that point of intersection, your Q stays the same, I stays the same. So the only thing which changes is this T. From 300 now it becomes 15 mm over here. So let's make a note of that. If you substitute the numbers for this one, you will get the value of tau at B. So you see the increasing jump that you have. The moment you move from B prime to B, your shear stresses essentially shoots up. From 1.13, it goes to this jump of 22.6 MPa. So let's maybe mark these ones over here. So the top one is tau at B prime, and this is the tau at B. Now, last thing which is remaining in our points of interest is the centroid C over here. So for the centroid C, we are going to consider this entire area that is there. You can break up into two individual chunks when you calculate the Q. You can calculate the Q for this one. Remember, we had seen that when we have cross section which is just not one uniform rectangle, you can calculate the Q for this and for this bottom part over here. This one, let me mark that as well. And you can add that up. So it is essentially for this top rectangle, it is a prime y bar prime, and this bottom rectangle a prime y bar prime, and then you add it up to get the total Q. So you can go ahead and do that. So for that, what you will get, the value of Q is so let me just mark that at C. So at C, you get is the value of Q, and again you substitute in the same formulation that is there, that your tau at C at C, we get tau of C as 25.2 MPa. So let's again jot down the main regions we saw. So first, at the top and the bottom, it is 0. At your B prime, it is 1.13 MPa. At B, it is 22.6 MPa, and at C, it is 25.2 MPa. And we know, since these are sections are rectangle, you will have a kind of a parabolic variation that is there. So let us draw the variation across this entire section. So I'm going to draw for this section in a 2D diagram from when I'm viewing from this side over here. So let's see how this variation happens. So at the top here, at the top in this part over here, it is equals to 0. Then at B, which is 1.13, then at B itself, just at B prime, just below B, I am going to have a jump which is going to 22.6, and then at C I will have 25.2. So these are the different ordinates of your shear stress. So at the top is 0, then you come down here, this is your point B prime. At B prime you have 1.13, and just to the below of B prime where you have the point B undergoing a jump, that becomes 22.6. From there you are coming to the centroid of the section C, so that is 25.2. Then again the bottom part is an exact mirror image of what you have at the top. So I hope with this example it is clear that how we derive the shear stress distribution across the entire section. Now remember that these values are not happening just at the edge, it is happening across this entire section. So this 0 over here is across this entire section, this 1.13 is across this entire section over here, at this C it is across this entire this small section that you see that you have 25.2 over here.